In Lesson 6.3, we're looking at similar triangles. You'll learn to identify similar triangles and use similar triangles to solve problems. How do engineers use geometry? The Eiffel Tower was built in Paris for the 1889 World Exhibition by Gustave Eiffel. Eiffel, who lived from 1832 to 1923, was a French engineer who specialized in revolutionary steel constructions. He used thousands of triangles, some the same shape but different in size, to build the Eiffel Tower because triangular shapes result in rigid construction. And I thought it was interesting, under the picture of the Eiffel Tower, they said the Eiffel Tower weighs 7,000 tons, but the pressure per square inch it applies on the ground is only equivalent to that of a chair with a person seated on it. Postulate 6.1 is the angle-angle similarity postulate. And remember, a postulate is so basic that it cannot be proved. We'll use it to prove theorems. Okay, the angle-angle similarity postulate says that if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. So in this diagram, because angle P is congruent to angle T, and angle Q is congruent to angle S, well, there's only 180 degrees in any triangle, so then the third angles must be congruent also. So the two triangles have to be the same shape. And that little tilde, remember, means same shape, similar. So these two theorems flow directly from postulate 6.1. The side-side-side similarity postulate: if the measures of the corresponding sides of two triangles are proportional, then the triangles are similar. So it's like side-side-side triangle congruence, only we have the word proportional instead of congruent. And 6.2, the side-angle-side similarity postulate: if the measures of two sides of the triangle proportional to two corresponding sides of another triangle and the included angles are congruent, then the triangles are similar. If you're interested to see the proof of Theorem 6.1, it's on page 299 in your book. It's a nice paragraph proof. They got a little carried away on example 1 with the amount of information they gave us. They already marked on the diagram that AB is parallel to CD, and I marked that BE is 27, and since BA is congruent, that would be 27 also. And DE is 45, so that would be 45 also, since they marked that congruent. And AE is 21, and CE is 35. Determine which triangles in the figure are similar. Well, it would be the two isosceles triangles. So we could use the parallel lines to say that if AB is parallel to DC, then alternate interior angles must be congruent. So angle BAC must be congruent to angle DCE by alternate interior angles. And we can see that these two angles are vertical angles. So we could use the angle-angle similarity theorem to say that triangle ABE is similar to triangle CDE. Since they gave us these side measures, we could have also found the proportions. So 27 is one of the legs of my isosceles triangle in the small triangle is to 45, as 21 is to 35, and we would have, if we divide the first one by 9 over 9, divide the second fraction by 7 over 7, I get 3/5 and 3/5. So since all three sides are similar, since it's isosceles, I only had to do that once, I could say those triangles are similar by the side-side-side similarity theorem as well. Well, I guess we could have also used side-angle side. Since we had all three sides and we've got at least two angles, I could have picked either one of those angles and said that was the included angle. So all three of my methods of proving triangles similar work on this example. And I thought I should add and point out that the way I marked the angles actually is purposeful. When we name similar triangles, just like congruent triangles, the corresponding parts need to be in the same order. So A had one arc, B had none, E had two, C had one, and then D had none, E had two. So once I committed to the order of A, B, E, C, D, E had to follow. And just in case you're wondering why, yes, the reflexive, symmetric, and transitive properties are all true for similarity as well. And this is a theorem, so that means all three of those can be proven. For example 2, we're given that segment RS is parallel to segment UT. So that means our alternate interior angles are going to be congruent again. And RS is 4, RQ is x plus 3, QT is 2x plus 10, and UT is 10. They asked us to find the lengths of RQ and QT. Well, because of angle, we just show that the triangles are similar. Let's write that out in order. So we'd have triangle. If we do RSQ, that would force the order for the second one. R had one arc, so that would go with T has one arc. And then I did S has two arcs, so I need U, and then Q has no arc, so it has to be last. It's helpful to write that similarity statement because now that helps us line up our similar parts. I could say RS is to TU. Okay, here's RS and here's TU. So here's RS, here's TU. See how the similarity statement helps us line it up? Okay, RS is to TU as RQ, okay, is to, RQ is first letter, last letter, TQ. And let's look at it on the diagram also. So here's RQ and here's TQ. Okay, that's going to help us set up the nice little equation. RS was 4 and TU was 10. RQ is x plus 3. And TQ is 2x plus 10. When we do cross products, we're going to have 4 times 2x plus 10, my plus kind of failed there, equals 10 times x plus 3. It's the product of the means equals the product of the extremes, or numerator times denominator equals numerator times denominator. Okay, then we get to distribute. 8x plus 40 equals 10x plus 30. I want to get my variable on one side. So I have 40 equals 2x plus 30. Subtract 30 from both sides, so 10 equals 2x. Divide by 2, x is 5. And they ask us to find not x, but the length of RQ. So RQ is x plus 3, so 5 plus 3 is 8. And QT is 2x plus 10, so 2 times 5 plus 10. 10 plus 10 is 20. Our next problem is a shadow problem. And in shadow problems, we assume that a right triangle is formed by the sun's rays from the top of the object to the end of the shadow. So I don't know what that's supposed to be, a post or something. We assume that it's going straight up and down. It's not at an angle. Trees sometimes go straight up and down, sometimes go at angles, but we assume for this book that they always go straight up and down. Josh wanted to measure the height of the Sears Tower in Chicago. He used a 12-foot light pole and measured its shadow at 1 p.m. The length of the shadow was 2 feet. Then he measured the length of the Sears Tower shadow, and it was 242 feet at that time. What is the height of the Sears Tower? Okay, I went ahead and stuck this study tip in here because the way they drew the diagram, they made it look like overlapping triangles, which it probably wouldn't be in the real world. But this is a good tip. When two triangles overlap, draw them separately so the corresponding parts in the same position are on the paper, then write the corresponding angles and sides. So instead of their lovely drawing here, let's just sketch. There's my 2, there's my 12, and then I'm not drawing to scale. 242 and X. Because both measurements were taken at the same time, we can assume that the triangles are similar. That angle is going to have to be the same angle of elevation of the sun. And so one of the ways we could set it up is the way they did. They have the height of the tower, which we don't know, is to the shadow length, which they measured as 242, is the same as the height of the pole, which we know, and the shadow length of the pole, which we know. So we can do cross products again. So we have 2x equals 12 times 242, and we'll divide both sides by 2. I'm going to let my calculator do all the heavy lifting here. There's no point of getting that product, really. Final answer, 12 times 242 divided by 2, I get 1,452 feet. Our big ideas for lesson 6.3 were that angle, angle, side, 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 and side, angle, side similarity can all be used to prove that triangles are similar, and the similarity of triangles is reflexive, symmetric, and transitive.